Okay. So we continue our discussion on Euler equation, which is the case for the inviscid flow, where you basically say that the viscous effects, the frictional force between two layers of fluid moving with a relative speed with each other, those effects are neglected. And today, under a certain condition, we shall be also studying potential flow. Basically, potential flow is the case when the curl of V is zero at every point in space, except maybe at some singularities. And then you can write down the velocity field as a a gradient of a scalar field called the velocity potential. And if you take the gradient, you get the velocity field. And of course, if you're working with a scalar potential, it's much easier. And we shall be solving some uh, we'll be calculating the this velocity potential for certain very simple cases, and combining those, look at certain complex flow fields. So yeah, so you find the actual use of it only at the end of the lecture, right? So let's go on. So basically, I'm just telling you that the Navier-Stokes equation, which we shall work with the next week, is basically the total derivative of the momentum field, right? Rho into Vf, where Vf is a function of x, y, z, and t, and the total derivative is this partial derivative with respect to time, as well as rho into v dot grad. So this is a dot product, and this operator is acting on the velocity field. And this is the viscous term, which we are going to neglect for the Euler equation. So eta into grad square Vf. And how does it come? We'll see next week. And minus grad P is what you have seen in the previous class, and minus rho plus rho into velocity per unit volume. Sorry, force per unit volume, right? And if you integrate over the entire volume, you'll get the total force. So this is the Navier-Stokes equation in the simplest form for simple fluids. And of course, you can have complexities, but we're not talking right now. But even then, for Euler flow, we're going to drop this term. We're going to say that eta grad square V is equivalent to 0, right? I said the word equivalent to, because real fluids always have a finite viscosity, except for superfluids. So we're going to discuss when these equivalent to 0, to making this approximation is a valid approximation, and under what cases shall we uh, study it. So under what cases we can study it can also be understood if we write down the dimensionless form of the Navier-Stokes equation, which again we shall do next week. So after we have done that, how and when it can be dropped, it will be more obvious to you. And you should revisit this place. But just to tell you, yeah, so this is the dimensionless form, where basically if you had a certain length scale over which velocity is varying, or you had an obstacle, that length scale, and a certain time scale which can be defined. So if you make it dimensionless, if you divide by a certain time scale of the flow and a length scale of the flow, so that this V becomes measured in those units, so this V dash will also become uh, in, I mean, it will be suitably non-dimensionless. And what you see here is the so-called uh, viscous term, and that can be written as, so U is a standard velocity, the characteristic velocity of the flow field. L is the characteristic length scale. Rho is the density, right? Assuming incompressible fluid, right? Uh, and this quantity eta by rho UL or rather rho UL, and you bring it down in the denominator. That's the Reynolds number, as you will see, and that will play a very extremely important role. So this quantity is essentially 1 by the Reynolds number, right? And what I need to discuss is also, whereas eta is the viscosity. Now eta by rho is also called the viscosity. Okay, so eta is the viscosity or the dynamic viscosity, and eta by rho is the kinematic viscosity. Why am I discussing this? Because I want you to notice this equation. And if you had no pressure gradients and these terms, so this is essentially a diffusive equation. If you note, this is a diffusive equation, and if rho is suppose a constant, it's not changing, it's incompressible fluid, then eta by rho is something like the diffusion constant. Except now, this is the diffusion constant for momentum diffusion. Like previously, you might have come across d as the diffusion constant of certain molecules, but here you are really talking about the diffusion constant of momentum transport, momentum diffusion. Note there is a diffusion equation in case any of you haven't done the computational physics course. So there is a diffusion equation because there is a single derivative with respect to time and a double derivative with respect to space. So this forms, so ddt of a certain quantity and correspondingly grad square of the same quantity, right? This is a row missing something. I'm not sure. Uh, yeah, no, it's not missing. Basically, this row will come here, and then it will be a diffusion of the velocity field, a momentum field, if you like, multiplied by rho on both sides. So this is the diffusion constant, and then this kinematic viscosity is acts like the diffusion constant for moment transport, and this will become important just in the next slide. Uh, okay, the Euler equation, you've come across it, looks like this. This, when you're writing it, v dot grad into v, it assumes an incompressible uh, fluid, which means divergence u equal to 0, right? And we're going to work with these aspects. Uh, when is Euler equation valid? It's of course valid for a superfluid with which has actually 0 viscosity, and then you can write this equal to 0. And liquid helium at temperature less than 2.17 Kelvin is a superfluid. But you can also apply Euler equation to study flows for real fluids when there are non-stationary. What does non-stationary means? Time-dependent flows for short time intervals. Suppose you have made a certain very quick change in the boundary conditions for which the velocity field starts changing, but you are looking at velocity fields when momentum diffusion hasn't taken place over the length scale of the entire fluid. Then momentum diffusion hasn't taken place at short time scales where the length scale of the flow or fluid is such that momentum hasn't moved diffusively from one end to the other. There you can use Euler flow, uh, Euler equation of motion. How and why you're going to see much later, right? But I'm just telling you, I mean, since you're doing Euler's flow, Euler equation, you need to know where it can be applied and why you are studying it. Euler equation is also valid at large distances from boundary walls if the bulk flow is not turbulent. Okay, so near the boundaries, you will have stick boundary condition, and there will be very quick, um, a very a, 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 large velocity gradient. and there will be a large velocity gradient, momentum diffusion uh, over that length scale. Actually, you create a velocity gradient. But if you're looking at large distances, much larger, over which diffusion um, of momentum affects, then you can use the Euler equation. If fluid is being perturbed at extremely high frequencies, very short time periods, and you're looking at flows at length scale much greater than nu, kinematic viscosity into time. So you're looking at length scales where diffusive transport of momentum hasn't taken place. There again, you can use Euler equation, right? So viscous diffusion phenomena hasn't set in at the length scales, yeah, so velocity fields are not affected by grad of v, which is this case. That's where you use Euler equation. How and why you have to wait. We in this today's continuation of the lecture, we are going to mainly see the consequences, or what are the kind of flow fields, what are the kind of calculations uh, where the effects of viscosity was equivalent to zero. And as you have seen previously, that if a flow field is irrotational at time t equal to zero for the Euler equation, it will remain so at all times, because this vorticity is a consequence of uh, viscosity. Okay, so for irrotational flows, once it is irrotational, it will remain irrotational because viscosity is zero. Uh, Curl of V equal to zero. And if curl of V equal to zero, then it is called potential flow. Why? Because if curl of V equal to zero, V being the velocity field, of course, then the velocity field can be written as grad of phi r, velocity potential, right? Because curl of a gradient of a scalar function is always zero, right? So that's why you can write it as a velocity potential. I'm using this symbol phi, but I want to highlight that this is capital Phi. That's why I put this in red, and that is not to be confused with the phi that you have seen, which is the phi, the potential function from which conservative force fields can be derived. You have seen the Bernoulli equation in the past, where we wrote in the past that rho v square by 2 plus p plus rho phi. This phi was coming from the potential of a conservative force field. Uh, so whereas here we are using the velocity potential capital Phi, and the Bernoulli's equation uh, in Euler flow, where viscosity is neglected, in this case will become rho del capital Phi del t. So this quantity, the previous two terms, kinetic energy, density, pressure, and uh, yeah, this rho into phi was what was maintained constant previously. For steady flows, that's what we had discussed in the past. But now, if the flow is itself changing as a function of time, then this term gets added, right? We are not considering steady flows anymore. Uh, so del phi del t will be the appropriate term. Of course, we have divergence v equal to zero, and since v can be written as grad of phi, you get Laplacian phi equal to zero. And that's a very nice thing, because from your electromagnetism course, you have learned how to solve Laplacian phi equal to zero for different boundary conditions. Moreover, people who have done the computational physics course, where analytically things become a bit more intractable, even there for very complex boundary conditions, you have learned how to solve grad square phi equal to zero. And even if you haven't, don't worry. I mean, but Laplacian phi equal to zero has very nice properties, and uh, we know how to handle that. So in Euler equation for irrotational flow and incompressibility condition, this holds equal to 0, and this now is a system. If you have to specify the boundary conditions, you can easily solve for the scalar field and thereby get the velocity field. So that's very nice. But you will see that in the discussions that we'll have simple velocity fields, and from there get the scalar fields to develop an intuition and then complicate the system and do the reverse. Okay, so be prepared that for some time to discuss, we're going to take simple velocity fields and calculate phi, but later we are going to complicate the situation. The boundary conditions, the simple boundary conditions will be, if there are any boundaries, then no boundaries can cross the boundary wall. So which means that the normal component of the velocity at a boundary wall will be 0, and del phi del n, the consequence, the velocity, so normal component of the velocity, that will be del phi del n, the grad in the n direction, the component in the normal direction, that will be equal to 0 at the boundary surface. In the absence of viscous forces, we cannot have any prescribed boundary condition for the tangential component. If there were viscous forces, basically the viscosity ensures, especially for macroscopic flows, that the velocity at the boundary sticks to the surface, the fluid sticks to the surface at the boundaries, and that means the fluid is moving with the same velocity as the surface of the boundary. That means in the no slip or the stick boundary condition, the tangential velocity of the fluid is equal to the velocity of the surface. That's the so-called no slip or stick boundary conditions, because the fluid is sticking and moving along with the surface. So that's what happens when there is viscous forces. But in the absence of viscous forces, uh, we have to adjust, and depends upon the situation, we'll take care of it, we'll discuss it. Okay, so these are the boundary conditions. uh, Now, from your electromagnetism course, you might already know that if grad square phi, um, q and rq is charge, well, I have put a vector sign, but I think I wanted to say in terms of uh, charge, right? Um, so if that is equal to 0, that means if you're solving for phi in a charge-free space, you can find the solution, and moreover, phi will be unique and well defined, as a consequence of which the velocity field itself will be unique and well defined. Okay. So with this background, what we do is try to find velocity fields analytically, or rather phi fields analytically, under various conditions, without having to resort to complex computations. And we'll take some simple cases like uniform flow, vortex flow, some sources and sinks, a, a point where fluid is emanating, is being introduced into the XYZ coordinate. Sinks is a point where fluid is flowing out, been taken out like in a drain's tiny hole. Um, uh, right? So these are very simple and simple cases where you can calculate the velocity field and thereby the phi. Using that, we are going to do dipole flows where you have a source and sink in close proximity with each other, and that idea is in turn will be used very simply and elegantly to look at flow around a circular cylinder or flow around a sphere, right? So here we are going to basically, we know the phi's of these cases. Using that, we're going to calculate the phi of this, from which we shall get the velocity field, and then use that to look at these two cases. So that's where we are heading for, just to know. This fluid mechanics, as you're seeing, is a bit of mathematical course, but finally we're doing physics. So we need to know what is the physical picture, where are we heading, what are we explaining. So that's important, right? I mean, I don't know whether it's important for you, it's very important for me. Just for ease, I have written down the gradient divergence curl Laplacian in cylindrical coordinates. I've copied it from somebody and some from some place, and I already see that there are spelling errors. And similarly, gradient divergence curl and Laplacian in spherical coordinates, which you can quickly refer to, and even I can refer to as I go on. Okay, with this, let's look at, suppose these are two boundaries, there's no viscosity. So you have uniform parallel flow in the x direction. If you had viscosity, the fluid velocity here would be zero, and fluid velocity here would be zero, because the boundaries are stationary, the fluid would stick to the boundary walls. But we are looking at inviscid flows, Euler equation, and as a consequence, you can have infinite. You can have infinite velocity ground gradient at the boundary. So the entire flow is moving with uh, finite velocity, because yeah, because this is, and in this case Vy equal to 0. If we have such a flow field, which is possible for a superfluid, then del phi del x will be equal to u, because we take the gradient of phi. uh, you will have, you get the velocity field, and you are specifying the velocity field and trying to get phi, and that is phi is equal to ux plus c. So if you had to plot phi, how would it look? At a point x1, you would have a certain value phi1, whose value will be ux1 plus c, say. Then here you will have value phi2, ux2 here. It's a different value of u. And yeah, so it doesn't depend upon y in this direction. This will be a, it will be equipotential, if you like, along this direction. But along x direction, it is going to have different values. Phi3 here would be ux3. So phi is increasing, if you like, or changing in this direction. And of course, if you take the gradient, you will get the velocity field. So that's the velocity potential. Just so that you don't confuse, there was also the stream function when uh, divergence of u was equal to 0. Stream, so that that stream function essentially came from divergence u equal to 0. Uh, and if you had to calculate that, to remember, del phi del y was equal to u. Here, del phi del x is equal to u there, so that it vanishes. Uh, Divergence of u vanished, and had to consider 2D flows in 2D. Then del psi del u del y was equal to 0, and psi was equal to uy. Here phi is equal to ux. Remember the difference, right? In cylindrical coordinates, suppose we are looking at cylindrical coordinates and we wanted to do the same calculation. Uh, Remember, v equal to basically grad phi. We are coming back and talking about the velocity potential, and we are taking, suppose we are taking, I mean, the velocity fields are all in the x direction. It's up, or if you're talking in cylindrical coordinates, you can align the cylinder such that it's in z direction. This was a cylinder, this was two plates, right? There's a difference. This is the z direction now. Now, if you take the expression for gradient in cylindrical coordinate, you are saying that there's no theta dependence along as you go around the origin. There's no dependence. So basically, you have this term and this term, right? So I've written del phi del z equal to 0. and u is equal to vz, right? So del phi del z gradient, taking the gradient, is equal to u, and that is equal to vz. Then phi is equal to v u into z plus c. And along the radial direction, del phi del rho, rho being the cylindrical r coordinate, that is equal to 0, phi equal to constant as you move out radially. There's no difference. So this is how it is in the cylindrical coordinate. Now you can also calculate, just for comparison, not to confuse with potential flow, you can also calculate the stream function psi in uniform flow in cylindrical coordinates, right? And that's useful only for 2D flows, just reminding you. And if you have forgotten, please refer to week 2, lecture 2, slide number 18. And there, to get your divergence u equal to 0, we have to define the stream function such that the velocity field, right, uh, in the z direction vz was 1 by minus 1 by rho del psi del rho, because that was the velocity field in z direction. We have to take del psi del rho 1 by rho, and that's what we have here, right? And from there we get the stream function to be minus u rho square by 2. Note the difference from here, which is velocity potential, right? And the other one, del psi del z, which would give the u in the rho direction, the flow along the rho direction. Here it is 0, so when you integrate it will be just constant, right? So similarly, I can ask you to calculate the stream function for spherical coordinates for uniform flow, of course, uh, right? So that's what you can do. uh, uh, now now we just go to a slightly different case, the sources and sinks, and we're going to work in cylindrical coordinates. Now just imagine that there's a certain source term, so fluid is being gradually introduced at the origin and it is flowing out radially. The z plane is perpendicular to the plane of the paper, right? And at each point along z there is a flow, a certain amount of fluid which is being introduced, basically, right? So elementary flow streaming at a rate of flow q. So every unit of time, rate of flow, unit of time, volume q is being introduced, which is flowing out radially outward. No theta dependence and no z dependence, because at every point in z you are introducing a certain quantity of the fluid. So the velocity flux, if you like, and you, for that you need an area, so dl, and you are taking a dimension in the z direction, dl dz, dl is rho d theta, rho d theta equal to dl. In the z direction, that's the surface area pointing out radially, right? So v rho, so I've given rho hat, right? Uh, Rho being, by the way, the cylindrical radius direction. So it's a bit confusing because density of, yeah. So there is a velocity field. Velocity flux is v rho, which is in the radial direction, into dl dz, again rho hat, because this area, the normal to this area will be in the rho hat direction. And so total flux, okay, total flux, uh, the volume which is being transported out, of course you can multiply by rho of fluid to get the uh, mass flux. But so rho d theta into dz equal, this is equal to q into dz. At every unit length along the z direction, you are introducing q amount of fluid, rate of flow, q, right, over length dz. In that case, you get v rho, the velocity of the fluid in the radial direction. It decreases q by 2 by rho, rho being the radius vector in the cylindrical coordinates. No theta or z dependence, as I said, right? Now, the aim is to calculate the velocity potential, right? We want to calculate the velocity potential for source and sink, then combine it to make more complicated cases, to look at more complicated cases. So at the moment, our focus is we have got the velocity field, we are calculating the velocity potential. Though we defined velocity potential, because in more complex cases, it might be easy to solve for a scalar field and get the velocity field, and we shall do that. But at the moment, our aim is to calculate the velocity potential. Now, you know that the gradient of the velocity potential is the v rho, right? And here we have velocity uh, flow only in the rho direction. So we just take the expression del phi del rho, the gradient in cylindrical coordinates, and that is equal to q by 2 pi rho. So the velocity potential becomes q by 2 pi log rho, and rho 0 is some arbitrary constant. So this is the velocity potential. Uh, just so that you don't confuse, you can also calculate the stream function for such a system, then for a source. And of course, source, the stream function is very different. It was coming from divergence v equal to 0, and for 2D flows. And this is a 2D flow because it's flowing along this plane, right? There's no z dependence, no theta dependence, and so on. So there you had to write down the divergence expression in cylindrical coordinates, which is this, right? V rho and V theta. And this will be identically equal to 0 if you choose V rho to be 1 by rho del psi del theta. This rho will cancel this rho, and V rho, you are going to write del psi del theta and then del rho. So you have a rho derivative and a theta derivative. And similarly, V theta, you're going to define it. If you define V theta to be del psi del rho with a minus sign, then again you will get a double derivative in theta and a derivative in rho, and these two terms will exactly cancel. So what is the message? You will get V rho equal to q by 2 pi rho. V rho equal to V rho, which is equal to q by 2 pi rho from here, and that is equal to this term. So you can solve for psi, and that is dependent upon theta. Right? This is the stream function. But at the moment, I'm just putting it next to each other so that you don't confuse. One is the velocity potential and one is the stream function. The velocity potential for cylindrical coordinates looked log rho by rho 0. The stream function, on the other hand, is dependent upon linearly dependent on theta, right? And of course, you can do the same calculation for source flow in 3D, where you can check that the velocity in the radial direction will be q by 4 pi r square using the same principle as here. Here you use the symmetry of cylindrical coordinates. There you have to use symmetry of spherical coordinates, and you'll get 4 pi r squared, and then continue the same calculation, which I can give as an assignment problem or give it in a quiz, right? Okay, with this, we start doing something useful. I mean, not that the previous thing was not useful, it was useful to study more complex cases. And we're going to look at dipole flow using cylindrical coordinates. So we're going to use the phi expressions which we have derived here for cylindrical coordinates. So what is a dipole flow? Now, previously the origin was at the position of the source in the sink. Now the origin is here and the source is here and the sink is here. So this is R2, where the source is, the sink is R1, right? And if this is R2 and this is, you can just check that R2 plus R2, sorry, R minus R2 is R vector, right? So from the origin, from the origin you want to find the potential at a certain point, which is this, which is vector r from the origin, but you have to calculate the expression which we have defined, which we have derived, is from this point. The velocity potential, right? You have to consider this vector at this point r is q by 2 pi. There's a certain flow rate, volume of fluid which is being uh, given out at this point, r minus r2 by r0, some constant r0, integration constant. And from similarly from the sink, you are going to get minus, because it's absorbing, q by 2 pi r minus r1 by r0, which is the constant of integration. Now, if you wanted to find the total scalar field velocity potential here, you just add these two, right? You just add these two, and which will be q by 2 pi, this plus this. Now, the book Physical Hydrodynamics has used such an expression to expand, but I found it a bit inconvenient. So what I did is take log r minus r2. Just one second. I'm recording. I'll call back later. So what you can do is, if you stare at this, basically I have done a Taylor expansion suitably log 1 plus x equal to x. Um, right, I mean, here I've broken it up, and here I've used log 1 plus x, and similarly for the other term. And when you add these two terms, you get r1 minus r2 by r cos theta, right? And this is modulus. So using this expression, so basically these two terms give r1 minus r2 by r cos theta, right? Where yeah, where cos theta is basically this angle. You can just try it out, uh, right? You can just try it out. So then you get essentially minus q by 2 pi r r2 minus r1. Remember, there was r1 minus r2. Since I'm writing in terms of r2 minus r1, you get a minus sign here. And this q r2 minus r1 you write as p. Like something like a dipole moment, except it's not charge, but this is q, the flow rate. So as a consequence, phi equal to q by 2 pi r1 minus r2 r cylinder. I'm just reminding you, this is in cylindrical coordinates, not in spherical coordinates, cos theta. And then when you write it in terms of r2 minus r1, because that's how p is defined, then you get this minus sine p cos theta upon 2 pi r cylinder. And this in turn, this cos theta can be absorbed as p dot rho. Rho, okay, I've used mixed up. So this r is rho. I'm just writing it. Uh, so this cos theta, p dot rho, right? And then I'm reminding you, so this is r square. But if you write it in terms of cos theta, this is r cylinder, right? Because just this r cylinder. Whereas if you write in terms of r vector, get a rho square here. Okay, so now you have found out a scalar velocity potential scalar field for a more complex flow. Take the suitable derivative to get v rho, which is p cos theta upon 2 pi r cylinder. I'm just reminding you, this rho, we are working in cylindrical coordinates, whole square, right? And again, v phi for a dipole flow is p sine theta 2 pi r cylinder square, right? Uh, just in case you are confused, R1, if you have this R2 minus R1, it is going to point from here to here. So this is the direction of P, the vector of P. Why is that? In case you are confused, suppose this was R1, any point R1. Again, the people who have done computational physics, they'll have it easy. This is R2, right? Then R1 plus x equal to R2, or x equal to R2 minus R1. If this was x, R2 minus, so yeah, so R1 plus x equal to R2, x equal to R2 minus R1. But what is the direction of R2 minus R1? It goes from point 1 to 2. So R2 minus R1 here points from here to here. Remember the direction. And then dot rho, or r in the cylindrical coordinates, that's what's here, right? Or if you write it in terms of cos theta and sine theta, you get r cylinder square, right? uh okay, so you can also of course do so this previous calculation was done in cylindrical coordinates, but you can also do the entire thing in spherical coordinates. So if source was spreading out in a spherically symmetric manner, then you can calculate of the the spherically symmetric radial velocity field as q by 4 pi r square by using very similarly uh, the, the current, the flux essentially, which will be rho L VR, and then you use your 4 pi r square, you integrate over the surface area, and you'll get VR equal to q by 4 pi r square. Then very similarly, you can calculate the phi for a source, then calculate the phi for a sink, and then you calculate a dipole. So suppose you have in radial coordinates a dipole. This is a small distance where you have a sink here and a source here, and do the entire calculation just as before. And in spherical coordinates, you will get VR equal to p cos theta by r cube, where r is now in spherical coordinates. And v theta, you will get again r cube in uh, spherical coordinates. And of course, we can. This is an assignment, and we can use this as a quiz problem. Okay, so I'll end here and we'll continue later. Stop sharing and then stop recording.